Welcome, baby stats. We're doing the second lesson of Unit 7. Sorry I can't be with you today. We're talking about sample proportions. Let's get into it. So we're talking about p hat and how good of an estimator is it for the parameter p. And p hat's a statistic, p is the parameter for the population. So we're talking about a sampling distribution of p, of the population. So now we're looking at some Reese's Pieces cookies or candies here. We're going to talk about this sample distribution first, okay? And at the end, I'll share an applet where you can go and simulate this. And I apologize for it's a little blurry. So we have Reese's Pieces. We're going to take simple random samples of the candies, and we know that the proportion of orange candies is 0.45. So our first sample, we're going to do 25 as our sample size. So and lowercase n is 25. And they did 400 samples, and this is the distribution, the sampling distribution that they got. Okay. And if we notice a few things, that the mean of this sampling distribution is 0.448, which is very, very close to 0.45. And the standard deviation is calculated here, 0.103. Now, what would happen if we change our sample size? So now our sample size is 50. So now we're looking at this sampling distribution. If we look at the overall shape, it's not too different. Obviously, they're different distributions, so it's not going to be identical. Again, they did 400 samples. Our mean this time is 0.451, which is much closer to p, so p hat. Our mean, our mu p hat, is very close to p. And our standard deviation is 0.0068. So our standard deviation got much smaller. Here our standard deviation was 0.103. So when we describe the distribution, right, we talk about things, remember CUS. CUS is going to be this describing the center. Well, the mean of the distribution, mu sub p, is p, right? And we saw that our mean, mu p hat, is very, very close to the actual population proportion of orange candies. It is an unbiased estimator of p. Okay. So then we're not talking about u because there's not a lot of unusual features here. But let's talk about the shape. So it looks like it's approximately normal. Okay, and we'll talk about some rules for saying that we're going to use and follow to determine if we can use a normal approximation to approximate the sample distribution. Okay, and then we talk about the spread. So you notice that as our lowercase n got larger, went from 25 to 50, our standard deviation shrank significantly. So our standard deviation is going to get smaller as our sample size gets larger, and it depends on the values of n and p hat. Okay, now we have some equations. So, and some things to remember. The mean of a sampling distribution p hat is p. That's it. So mu p hat equals p, which is given to us as the population proportion. Okay. The standard deviation of the sampling distribution for p hat, so because we're taking each one of those samples gives us a p hat, and so the collection of all those p hats is our sampling distribution of p hat. So our standard deviation of p hat is the square root of p times 1 minus p over n. Okay. Now, independence condition. As long as this condition, the independence condition, is satisfied, we can use these things. So these are true as long as we can satisfy our independent condition. We can use the standard deviation formula. That means your population has to be greater than or equal to 10 times the sample size. So if you think about our Reese's Pieces, did we have more than 250 candies in the machine? Well, yes, then we can use this as our standard deviation of our sampling distribution. All right, then we change our sample size. So at first it was, is it bigger than 25 times 10? That was our first sample distribution. We used sample size 25. Then we changed it to 50. So are there more than or the same amount? Are there at least 500 candies in the machine? Okay, if so, then the independence condition is satisfied, and we can use sigma of p hat. We can use this equation for sigma of p hat. Okay. Now, as n increases, the sampling distribution becomes approximately normal. So before we can use the sampling normal distribution as our approximation, meaning the calculations using the normal curve, we have to check is n times p greater than or equal to 10. So in our previous case, it was 25 times 0.45. Is that greater than or equal to 10? And 25 for the first sample times 1 minus 0.45, which is 0.65. Is that greater than or equal to 10? And yes, it is in both cases. Okay. So if this is satisfied, we can use the normal curve for our calculations. If this is satisfied, right, we can use this as our standard deviation. What does that look like in practice? So I will read this example problem. About 75% of young adult internet users, I'm going to stop right there and say P equals 0.75. Age 18 to 29 watch online videos. Suppose that a sample survey contacts a simple random sample of 1,000 young adults. I'm going to stop again. And lowercase n equals 1,000. 1,000 young adult internet users, and calculates the proportion P in this sample who watch online videos. Okay. First question, what is the mean of the sampling distribution of P? Well, the mean is going to be mu P hat. And remember, that equals P, so it's 0.75. There's not much more explanation needed. This is what we talked about in the last slide. The next one, let's change colors here. Find the standard deviation of the sampling distribution of P. Check that the 10% condition is met. Okay, so the 10% condition was, is the population, capital N, greater than or equal to 10 times, pardon me, sorry about that. I could edit that out, but I probably won't. I lost my train of thought. Okay, is the population greater than or equal to 10 times the sample size? Or in this case, the other way to say that is, that's a perfect way to say that. So, is the population of all young adult internet users greater than or equal to 10 times 1,000? So, is it safe to say that there's more than 10,000 young adults who use the internet? I think so. So yeah, we're good. That checks out. So now, because this checks out, we can use our sigma of p hat. We use our formula as p times 1 minus p over n. The square root of that. So that's the square root of 0.75 times 0.25 over 1,000. And this, with some rounding, is 0.0433. So we found our standard deviation of our sampling distribution. Next question. Is the sampling distribution of P approximately normal? Check that the normal condition is met. So our first condition is, does n times P, is that greater than or equal to 10? Well, let's check. Is 1,000 times 0.75 greater than or equal to 10? Yeah, that's saying, is 750 greater than or equal to 10? Yes, but now we have to check the other way. N times 1 minus P, is that also greater than or equal to, not 100, sorry. Greater than or equal to 10. So basically, is 1,000 times 0.25 greater than or equal to 10? Yes, 250 is greater than or equal to 10. So yes, our sample distribution is approximately normal. Okay? Last question, let's go back to red. If the sample size were 9,000 instead of 1,000, how would this change the sampling distribution? So they're asking about the entire distribution. And so there's not going to be any unusual features. We're just talking about cus. without the U. So the center and shape, if we remember from studying the normal distribution, they remain unchanged. What does change, though? Our standard deviation will get smaller. And that's our spread, if you recall. And some of you may say, well, if the spread's smaller, doesn't that change the shape? Yes and no. Yes, but it's still approximately normal, so no. Last example problem. It's what they call a four-step problem. We'll see these in some practice today and also in future quizzes and tests. So, a polling organization takes a sample random survey of 1,500 first-year college students, how far away their home is. Suppose 35% of all, that's a key word there, first-year college students actually attend college 50 miles from home. When I hear all, I go, oh, you're talking about the population of first-year college students because you just said 35% of all. So P equals 0.35. What's the probability that the random sample of 1,500 students will give a result 2 percentage points of this true value? What are they actually saying? Well, they tell you right here. State. We want to find the probability that the sample proportion falls between these two values because this is 0.35 minus 0.02 and this is 0.35 plus 0.02. That's what they're saying by within 2 percentage points. This is the range we're going to be looking at. So, our plan. And remember, this is first years that attend college within 50 miles of home. Okay. So we have our simple random sample. Lowercase n equals 1,500. Okay. And this is walking you through a lot of this stuff. Our independence condition is met because is the population greater than or equal to 10 times 1,500? Yes, there's approximately between 1.5 and 2 million first-year college students every year. So I think it's safe to say that number is bigger than 15,000. Okay. Is the distribution approximately normal? Well, they check. N times P, that's 1,500 times 0.35. That's 525. That is greater than or equal to 10. N times 1 minus P, okay, is here. They plug in the values. That's 975. Okay, so it is approximately normal. We must do these things. It's not going to be spelled out for you, but this is just to speed the process along. You must do these things before you can use the standard deviation and normal approximation. So the first thing we're going to do, we need the mu, because to approximate normal, we need mu and sigma. Sorry, it always looks like an R. My apologies. So the mu is 0.35. Remember, the mean of the sample distribution for p hat is p. It's 0.35. It's an unbiased estimator of p. Okay. The sigma of p hat is going to be the square root of p, 0.35, times 1 minus p, 0.65. That's 1 minus 0.35, divided by lowercase n, which is our sample size of 1,500. This, with some rounding, is 0.0123. Okay. Now, I'll show you the first ways. First, if you're going to use the z-table, we need to standardize our statistics. So we take the mean. Excuse me. Hold on. Nope. I'm skipping a step. My apologies. We want to check the probability that 0.33 is between p. Oh my gosh, my eraser is just not. That's a highlighter. There we go. Sorry about that. Thank you. Okay, so we want the probability that our sample distribution from this one sample of 1,500 students is going to fall between these two values. So we want to standardize it so we can use the z-table. So our lower bound is going to be 0.33 minus 0.35, lower bound minus mu, divided by a standard deviation. It's going to give us a z-value of negative 1.626. And our upper bound is going to be z equals 0.37 minus 0.35 divided by the standard deviation. It's going to give us positive 1.626. Okay. And so we have our normal curve here. We're going to draw that. Okay. I'm going to use the standard normal, so our mean is now 0. And we have 1, 2, 3 standard deviations. Then we have -1, -2, -3 standard deviations back down. So negative 1.6 is here, positive 1.6 is here. We're saying what's the probability that we're in here? If you're using your calculator, that's normal CDF, okay? Negative 1.626, lower bound, upper bound 1.626. Mu is 0, standard deviation 1, okay? That's if you standardize it. If you want to use the numbers as they're given to you, lower bound is 0.33, upper bound is 0.37, our mu is 0.35, and our standard deviation is 0.0123, okay? These all come out to be about 0.8961. The table gives you 0.894 something, but it's very close to 0.89. Okay. There you go. So let's round now. Imagine you're reading a report to non-mathematicians that don't care about 3 significant figures, right? Past or rounding to the nearest thousandths place. This is just for this exercise. 90% of all the sample random samples of size 1500 will result within 2 percentage points of about the true population. So I apologize for the length of the video. I'm ill today and this was not planned. So doing the best I can with what we got. Watch it at 1.5 times speed. I'll sound a lot peppier. Check for your assignments. If you have any questions, you know how to get a hold of me. Good luck.